Okay, great. So I will skip the introduction of how Samon and I got together and how this project started. What I want to very quickly review is the basics of EEG and where we get our signal from. I then want to do a quick review of the sensors that might be potentially now or in the future applicable to the Neurhome. I will discuss quickly on some the idea of feedback loops and how we can consider them in terms of positive and negative feedback. And then I will give a truncated history of BCI and going towards the feedback that we consider in the building person interface. So first of all, this is a cut through the brain like this, sagittal, coronal, sorry, where one of the things we can very clearly see is this band of gray matter. We call this the gray matter. This is where all the neurons are located. And the white matter is the tracks that connects all the neurons. And it's the cortical region that we will be measuring with EEG, the outside. And the organization is very important of this, of the cortex. What you see here in the top left is the original drawings by Golgi, for which he invented a staining technique for which he got a Nobel Prize. And what you see here is a Purkinje cell with this gorgeous tree-like structure. And what is very nice is that 2 years ago, people were able to get their hands on these original stains and were able to now record them with electron microscopy and are able now to see actually what he was drawing, because at the time, obviously, there were no photographs. And one of the things here you can see is this very beautiful parallel ordering of the pyramidal neurons that you can also see now in the microscopic pictures. And here as well, you see some big pyramidal cells, and you see the dendrites and how they expand within the tissue and how they seem to connect with other neurons. And actually, Golgi was of the absolute conviction that the brain was a net. It was a reticular structure. So all the neurons were connected with each other and were communicating like that as one big organ. But around the same time, you had Ramon Cajal, was also using the same staining techniques, but he sometimes saw one unit only and then another neuron. And he was able to infer actually that neurons actually are not really connecting. They are, he was assuming, somehow distinct from each other, which became the neural doctrine. And this was a debate between the two of them that went on during their lifetime. They both got a Nobel Prize, shared for their discoveries, but they never talked to each other because of this. And now we can really, with, for example, viral staining, can really see this beautiful, again, parallel forest that we see in this outer layer of the brain. And it is this parallel orientation of these big pyramidal cells that allows us to measure EEG, because what we measure is once these neurons are spiked or activated by other neurons, their action potential is relatively stretched out over time, long enough for the activity of multiple neurons to sum, the electrical activity that is generated to sum up to a voltage that can be measured. So this would not be possible if either the neurons are not oriented in parallel or if they were not firing at the same time, which means that the activity that we're measuring from the scalp is actually always a summation of synchronous neuronal firing in a large population of neurons, between minimally 10,000 neurons all firing at the same time. So that also should give us a bit of a humility about what we're actually able to measure with EEG. And so what you see here is, for example, a patch of neurons firing at the same time, creating this electric field strong enough to be conducted through the cerebrospinal fluid, through the bone, through the skin, and then we're able to pick it up by placing electrodes at different places of this differential. But as you might know, every electric field also has a magnetic field that is perpendicular to it. And this is something we pick up with magnetoencephalography, which I will touch on shortly as well. So this is the basic electrophysiology of EEG. And it's been exploited now, especially in the last decade or something. I remember when the NeuroSky came on and the Emotive came in. And these are consumer EEG devices that are wireless. They are portable. You can put them on your head. And they have what is called dry electrodes. They press in different mechanical ways onto the skin so that this EEG can be conducted onto the sensors and can be measured. One thing that was clear for neuroscientists from the beginning is that these devices, because of the sort of the constraints of the mechanics of it, they generally all measure just the front of the head. Now, at the front of the head, there is a lot of muscle of the forehead. I mean, you can see the wrinkles, you can see the eyes that move that create electrical activity, what you heard in the movie. And so there's really a limited sensitivity and a limited coverage of those brain regions that we are probably really interested in, like sensory regions, visual regions, somatosensory regions, motor regions. They are in the back of the head or at the top of the head. This is a beautiful example where there's a little bit more on the top by EMAG, which is a Dutch university company, who also a little while ago made one version with solar panels to power 2 electrodes. But and then we have some high-end versions of the same principle where more sort of, there's a lot of mechanical innovation going on, trying to get these electrodes on the positions that might pick up useful information. And so all these ones that I've just shown you, like those are like the consumer ones. None of them actually would provide us with a sufficient amount of information to do anything useful with. They would be very good in identifying eye movement stuff. There's also one reason why there have been in the beginning a lot of claims of what it could do, but now what you see is that a lot of companies are now selling these products for help in sleeping, in relaxing, and there's not much EEG analysis actually going on, although some of them provide the ability to, for example, measure your sleep stage, the moment that you fall asleep or how well you sleep, because this sleep really creates really strong effects on the brain. You get slow oscillations, which can be picked up pretty much anywhere in the brain. Because EEG, by virtue of the fact that it has to be conducted through all these layers, and all these layers have different conductivities, is that the signal spreads out a lot. So you have to have a really big signal to be able to pick it up. But if you pick it up, you probably pick it up everywhere. So that's the case with sleep. So you have some beautiful examples and beautiful designs of integrated EEG in headsets marketed for health, for example, or sleep. This is a Korean version with nice earplugs. But so more serious companies or more expensive headsets, they allow you to measure activity from more relevant regions, like this kind of scary contraption, where you see all the mechanics involved in being able to actually press these sensors onto the head in the right places, which has different levels of comfort. This is maybe the most advanced version of these dry electrodes that press into the skin. They were at least contracted by the DARPA, by the American Defense Agency. But these become very expensive, and for the purpose of the Neurhome, this might not cut it, because who wants to walk around the whole day with this enormous heavy headset on? and not even regarding the fidelity of the EEG, because once you have like this heavy thing, you move around, it starts to move on the head, and it becomes a very noisy signal. So a lot of development is in reducing the effects of movement and eye artifacts and things like that. So in laboratories, when we want to do mobile EEG, we always end up using things like this, like these caps, these stretch around the head. They would form to every shape of the head, which is very important and difficult to do otherwise. And we use wet electrodes, meaning that we use conductive gel to make a connection. And this takes time to set up. So this is a very practical concern. But if you have the right situation, and even if you only use 1 or 2 electrodes, what I typically do in a music setting, it gives good signal. It stays connected wherever you go. It's comfortable. And for instance, here we used the GTEC system together with virtual reality, for decoding brain states, and in this project sending them into outer space with a radio telescope. So, but EEG is just extremely limited. I will just give you two final examples of new developments. Move myself around. So yeah, this was last year, where a paper showed a way to tattoo electrodes onto the brain. I once shaved my head for the purpose of an EEG performance. I don't think everybody wants to do that, but it's a great idea. And I should also mention work from Scott McCaig, who has developed ear EEG and developing sophisticated source modeling to actually have quite a good sufficiency in reconstructing brain activity from the scalp, just from implanted earbuds. But it is just, so yeah, and then another thing which is just very cool, something that we've been working on a lot, is the whole new development in open hardware for EEG, which allows all of us to experiment and develop our own futuristic scenarios, if you like. And one that we use a lot is the OpenBCI, which has either 8 or, if you want, even 16 channels, for which you can then yourself create 3D print or whatever you create your own headsets. So this is a 3D printed headset, again with springs that press these dry electrodes into the skin, we've tried it. It's really, really uncomfortable. It's painful after a short time, and it's clunky and it moves around. What we've sort of ended up with is 3D printed cases with touch-proof connectors where we can press in electrodes, which I don't know if you see my camera, where we can have nice cup electrodes that we can just plug in and connect with gel and tape wherever we want, on the top of the head, on the back of the head, wherever we want. So these designs are open source. You can find them, and it really made our life easier because the portability and the robustness, thanks to Robert. And finally, in this sort of open hardware biosignal measurement, we don't only have, not everything should be done with EEG, and these people in the Bitalino, they developed these boards where you can, we have separate sensors for electrodermal activity, EEG, ECG, EMG, as well as accelerometers and what have you. So this really is a really burgeoning market, and because of its open source nature, it can develop really quickly. So this is really, really exciting. But EEG is fundamentally limited because of this conduction of the electrical activity. All the activity will be spread out. And honestly, to do more than simply turn on a light switch or have a one-dimensional interface, EEG will just not cut it, at least not in the future that we imagine, and certainly not for what we would imagine the Neurhome. So one step up would be magnetoencephalography. As I said, it measures, the brain also generates magnetic fields, and they don't have to be conducted through tissue. And so they can be picked up without any mixing of the sources. Typically, there's like 300 sensors here, and you can put it either sort of vertically or horizontally. The signal is really good, but as you can see, it's everything but portable. The reason is that this big hairdryer, this thing above the hairdryer, is a big thermos, and this thermos is filled with liquid helium to cool down the quantum mechanical devices, the sensors, to minus 270 degrees. So yeah, sorry for the bad picture, but you can imagine that this is not really portable, and actually it's increasingly expensive because helium is running out. So one thing that we were helping to investigate when I was back in Sweden was what's called high temperature squids. And high temperature meaning it's only like minus 170 degrees or something like that, made with liquid nitrogen instead of helium, which is cheaper, it's more portable. As you can see, it's only like a big thermos. So there's future in this, but the big future for MEG is in optically pumped magnetometers, which work with lasers and rubidium, because it turns out this rubidium changes its polarization according to the magnetic field. So if you blast a laser through it and you polarize laser and you measure the power on the other side, the amount of light, you can actually infer the magnetic fields. And so what you see here on the right side, on the left you have your original, on the right you have your optically pumped, is that things become suddenly much more feasible to wear. And so this is a wearable headset. The field is exploding now, and we will see a lot of developments here they're developing flexible headsets, for example, that can really strap on, for example, small baby heads, so that we can get the maximum amount of the sensitivity. But still, it needs to be very close to the head, because the further ahead you go, further away from the head you go, you lose your magnetic fields. So envisioning this for the Neurhome, it means we have to have extremely sensitive measurement sensors in the walls, as well as cancellation coils in the walls to cancel all the magnetic noise, which is already done in all the MEG labs, in all the MEG walls. We have big coils that work like sound cancellation devices. But to be fair, again, it stays limited what you can do, because more than 300 sensors will not give you anything more. There's just so much you can measure from the surface of the scalp, away from the scalp. So for real serious work, one needs to get, for instance, on the scalp. So EEG, electrocorticogram, is a strip of electrodes that can be placed directly on the brain, on dura. And of course, have a much larger fidelity and quality of signal. It's not really accessible to most people, though, and you would only do this really if you need to. So I think for now we can disregard this as a valuable method. What is really interesting in terms of BCI and brain-computer interaction interfacing is since the beginning has been the UTA array, which is this 10 by 10 grid of small sharp electrodes which are pressed into the scalp, into the brain, and have really highly detailed measurements of brain activity that can also be placed in very significant regions. So, for example, if you want to control a robot, you would place it, for example, in the motor region. Or if you want to look at the sensory regions, you place it just a little bit further up, like here, and you place it in the sensory gyrus, in the post-central gyrus. So this has been around since 2006, but this year they've developed a wireless version of this, and you see here this person with these UTA arrays implanted, with wireless connection in his house, and he's able to control Windows 10 and write letters and things like this. So while for 1-2 decades nothing much really happened, we suddenly are seeing this boom in the ability to take high density, high concentrated activity and transmit it wirelessly. And this UTA arrays since 2006, well, this year they came out with the sea of electrode array, which is a 72 times 72 is like over 5,000 electrodes. So you can imagine how much more information you can take from it if it already starts working with 10 by 10. And we can go even one step further. Last year, they developed the Argo, 65,500 channels electrodes on just a half a millimeter, half a centimeter, sorry. So these are, yes, they're invasive, but they are, for those paraplegic patients, for example, they are really a game changer. And they develop, they really increase quality of life. Now, in my work with epileptic patients, what we use is actually depth electrodes, because we want to target also subcortical regions. But this is one that is so far only used on animals, which is a 1 centimeter shank, but with many hundreds of contacts within it, spaced really close apart, so you get a gorgeous recording of all the layers in the cortex even. Also, you know, a couple of years old, but now very well used in laboratories. And one thing you've probably all heard of is, because how can't you, is the Neuralinks, the Elon Musk's company. Because these and yes, two innovations which can be considered innovations, like first of all these depth electrodes, and all these electrodes, they're rigid, you're right, and so having a rigid thing in the brain, I mean, it starts to either decompose, it starts to either move. You can only keep them in for so long. There's sort of inherent issues here, and what he proposes are these really thin filaments of nylon filaments with small contacts within them, which then can be flexibly implanted, and thousands of them can be attached to a preamplifier, and interestingly here placed on a USB-C key. Now, this has so far been used only on animals, but this is the second innovation, which would be the implantation of these wires via this sewing machine. And the idea is that rather than having to open up the skull or drill a hole in the skull, this can be relatively low effort procedure. Whether or not that's true or not, we'll see. But the first results are pretty impressive when it comes to the implantation. Here you see a zoomed in version and a rat wearing one of these heads connectors with 3,000 electrodes, and these small hairs all puncturing the or being close to the cortex. So that's sort of the idea that it's less invasive. Whether or not that's true, I don't know, but this is definitely one that potentially is much less invasive, and it's the stentrode. So it's a electrode that is implanted through the jugular vein, for example, and then once it goes into the arteries, for example, between the hemispheres, it's expanded and touching the outside, not blocking the air, the blood flow, but being able to record and stimulate the surrounding neurons. And I'll show you this. I found just in researching this project that this year they've successfully used this for the first time to have a highly efficient brain-computer interface where this person is able to navigate and click, double-click on Windows and write in Windows 10. So state-of-the-art stuff, which is non-invasive and implanted in the jugular vein. Well, maybe the final exciting electrode developed in Berkeley is this idea of neural dust. And so these are tiny piezo crystals, piezo devices that are together with a transistor are placed in arteries or in muscle tissue. And the electroactivity of the muscle tissue will change the way that these neural dust reacts to ultrasonic sound. So the ultrasonic sound is sent, and then the backscatter is registered, and in this backscatter, the changes there reflect the changes of electrical activity here. So they are still 1 millimeter by 3 millimeters big, so it's a bit too big to inject in the brain. but there's no reason why these won't sort of get into the nano size, or they have to be about 50 micron big to be useful, but they're already useful, for example, implanting in muscle tissue. And the good thing about this is that this material is non-degradable. So you can imagine in placing these in strategic places and having them with you your whole life. And there's no wires going through the skin or your skull. These will just non-invasively probed by ultrasound. So ultrasound is really an amazing innovation that has been occurring recently, and it's been used for many different things. For example, in the bottom line here, it's working with the neural dust. But it's, for instance, also used to open up the barrier between the blood and the brain to allow larger drugs and molecules to go through. And you can even use it for directly measuring brain activity, measuring the hemodynamic response, just like in fMRI. And actually, I placed a citation here in the bottom, where for the first time now this year, they've used this to decode the intention of monkeys to move and press a button on the screen. So before they're moving, the technology is able to detect this intention and where the monkey wants to move. So if we kind of summarize sort of like the potential electrodes and measurements that we have a whole collection which is just doesn't bring us the sensitivity and the detail that we want. Some are just too invasive, but we have a couple that have a really strong potential to be used for applications like in the Neurhome. And the only thing really that needs to be developed in a sense is the idea of more remote reading. And so I'm not a physicist, so I don't know how well this will go for the ultrasound. Or for the optical pump magnetometers, but these are potentially futuristic scenarios where these might be implanted in the wall of the Neurhome. So one important thing to consider when sort of responding to brain activity, especially, is this idea of feedback loops in nature, and to identify at least these two different kinds, either the positive and the negative feedback. So the negative feedback stabilizes the state of an organism, for example, in biology. For example, our thermoregulation, if we get too hot, we start to transpire, which then cools our body temperature again. Or if we get too cold, we start to shiver and we warm up again. So this negative feedback loop reduces change and stabilizes us. But then we have positive feedback loops where the change is amplified. So, for example, in childbirth, we have the fetus that presses against the stretch receptors of the uterus, which results in the oxytocin release, which then contracts the muscles in the uterus, which then increases the tension on the stretch receptors. And this starts to amplify until the contractions get strong enough to deliver the baby. Now, okay, so that was just a side note. A quick history on using the brain to control things. Not well known is the first one was Edwin Dewin, who was able to turn a light on and off back in the 60s. And I will send you this PDF, I hope, where you can watch the broadcast. It's amazing. And he was even able to create a Morse code system where he was able to write even with an error correction. It's really advanced work. He was also responsible for the first music piece made with EEG. And a decade later, Jacques Vidal introduced the term brain-computer interface and started up this lab called the Brain-Computer Interface Laboratory at UCLA. And this is a seminal paper where he talks about, you know, the potentials, the things we could measure, how we can use a BCI. And of course, a lot of it was the restrictions that their current hardware had at the time. You know, how much memory, how fast can they transfer information, things like this. Most of the problems are just not a problem anymore. And I think most of these problems are not a problem anymore. So really hardware is not so much the issue anymore when it comes to online brain EEG analysis. So, and it only gets less. So just to give you now it's much more of a nomenclature, you know, BCI, brain-computer interface. And the principle is as follows. You record, like, for example, EEG activity. You extract a meaningful physiological signal, of which you extract meaningful parameters, which you then use to, for example, decode the intention of the subject or the monkey, and which you can then use to control, for example, an arm, a robot arm, for example. And this creates then, of course, feedback, because the person will see the arm moving, and then via sort of positive and negative feedback, inherent in this system is able to navigate the robot arm. This was done, for example, here with a. This was done at Johns Hopkins together with the Defense Agency again, who developed the robot hand, and she was able, again with this Utah arrays, able to feed herself a bar of, himself a bar of chocolate. But back already in the 70s, you know, people were either concerned or like Burroughs or excited like Eaton in what this brain-computer interfacing could mean for also reaching a cognitive or mental or emotional state that would be desired. So here we're talking about this positive feedback loop. And for example, that would be a schematic like this, where we record, we extract these signals, but rather than using it to control something externally, we show the signal to the person, and then generally unconsciously they learn to control not their behavior, but somehow a electrophysiological signature. And the mechanisms are definitely not fully understood. But I want to show you, I want to cite at least this, my favorite paper on this, which is by the team of Hagwan Lau, which used this to, without showing the phobic object, in this case, for example, a spider, where people were phobic against spiders, instead of showing the spider, they showed the brain, they extracted the brain activity associated with the spider, and then people were able to downregulate their fear response, which didn't even occur because, you know, the fear had to occur after this primary process, and in thereby breaking the loop between the object and the fear response, and extinguishing the phobia. It's a remarkable work and remarkable application of this, which you know, I wouldn't believe 10 years ago. So when it comes to, for instance, the Neurhome being a place where also we are able to optimize the conditions of a person, we can also think of something which would be much more sort of be called neurofeedback than BCI on itself. Now, I won't have time to go into it, but we're using this a lot also in our musical performances, where instead of a visual feedback, we give a sonic feedback, and we use modular synthesizers to create a sort of person-by-person response to their brain activity. And in this, we've been very sort of inspired by also the whole modular thinking. So first of all, for example, this is one of our performances where we have two people being measured with two modular synthesizers, and they respond to the music, but also to the music of each other, creating this bigger sort of circular feedback loop, including multiple people. And here we performed this in London a couple of years ago. So here you see the modular synthesizer, which just became also a great metaphor for brain activity. Here is the sort of the modular script, if you like, the design of two of the performances, or rather the sound generation, the patch, where we have brain activity, splitting it in different frequencies, and having those different frequencies control different volumes of different sonic frequencies, filters, reverbs, things like this. And so by having this ability to modularize and to repatch, we can create a unique experience for every person. And I love doing this for people where every person I start with a blank slate, and we just develop, you know, a custom concert for everybody's brain activity. And so this idea that the mind is actually modular has quite a history and is in the end the basis of cognitive neuroscience. Now, let's say the last sort of development in BCI and decoding brain activity is the extreme power of artificial neural networks. So there's one way of decoding, which is sort of very empirically scientifically based, which is, you know, and that's how I'm trained. I know which signals correspond to which cognitive functions or cognitive modules, if you like, and then I extract those and I infer things from that, attentional state and things like this. But you can also imagine not having this focus and just having training neural networks to recognize certain cognitive states or emotional states. And for example, here we have the recurrent neural network, which is used a lot in BCI. Or we can also look at these more, you know, deep convolutional inverse graphic networks, which are used for Google for their image recognition. And as someone said, we envision something like this for the artificial intelligence underlying the Neurhome. And just to show you how powerful these have become in the last year, this is an amazing study where there were several phases, but the first phase, the neural network learned to recognize written letters, imagined written letters. So you give them an A and people imagine writing an A in their mind. Now, in the second phase, they were able, with these uter arrays, to read this sort of very early motor cortex activity and reconstruct the letter that people were intending to write in real time. So this person, and you see the example in the top bottom on the left, is real time writing a letter and the computer is extracting exactly what the person is intending to write. So what they use here is this recurrent neural network trained on, you know, the previous testing phase, learning phase. So all of this, taking all of this and we're taking a look at what we think is sort of a great imaginative tool that we've sort of came up with during this project is not a BCI, not a neurofeedback, but a building person interface with two aspects. One is that the building can respond to the brain state, but that brain state is not just a simple decoding of attention, of intention. It has also a psychological model. So what is interesting to know, and it's something that we still are at the beginning of, and this conference was definitely useful for this, is to understand how we react to different architectural or environmental spaces and to changes in that. So the idea here is that not only do we learn to decode the biophysical state, but we also learn to decode the reaction to changes in the environment and into the building, and thereby sort of are able to rather than enforce a certain single behavior, the buildings would be able to anticipate and to guide the brain state or the physical state towards a desired psychological state. I know this one is the most out there, but there is no reason why we can't sort of start to investigate what is the psychological effect of changes in the environment or in the building, and how can we anticipate and create those. So that is in a very short time, I'm sorry for the speed, what I wanted to sort of bring as a scientific background to what you just saw and heard. And I hope this gives us time to kind of go into a conversation and maybe explore some of these topics a bit deeper. So yeah, I guess can end by thanking everybody involved in this part of the project. Thanks a lot to the organizers of DNArchi. And voila, there's a lot more we can talk about, and I hope we get the chance.